Hi there. This is the last lesson in Chapter 9. So it's 9.5, fifth lesson on constant acceleration for the Year 12 bit of mechanics. So we're going to have a look at some harder questions. We've got all the SUVAT formulae now. We've derived every single one of the 5, so that's a case of applying it. So this lesson is going to have a look at 5 harder worked examples, and also we're going to throw in some laws of universal gravitation. Thank you to Mr. Isaac Newton. So that's just an extra bonus in a way included. So before we get into that, I want to give you the chance to get warmed up, as it were, to get fresh and thinking mathematically. So here's 4 warm-up questions for you to try. Press pause in a moment and try these on your own. When you're ready to see the solutions, press play and I'll guide you through how to get the answers. Okay, so let's have a look together now at question number 1. So for number 1, we have a particle P which is moving in the positive x direction with constant deceleration of 2 meters per second squared. At time t equals 0, the particle passes through the origin 0 with speed 10 meters per second. Find the maximum positive displacement of P from 0. So let's just label on what we know. So we're told it's moving in the positive x direction. It's got a constant deceleration of 2 meters per second. So at this point, I'm going to just add in SUVAT for SUVAT so that we can just add in what we actually know. So we know the deceleration is 2. Because it's a deceleration and is going against the motion, the acceleration is therefore minus 2. So at time t equals 0, the particle passes through the origin O with speed 10 meters per second. So because it passes through the origin, this is therefore the initial velocity, so this is u. So u is obviously therefore 10 meters per second. For part A, we want to find the maximum positive displacement, so we're after the displacement of P. So S is what we want to know. So I'm going to put this in a question mark. And we need to think as well, if it's moving along but slowing down because it's decelerating, the maximum positive displacement will be just at the instant before it turns back and starts to return to where it came from. So it'll be at the instant when the velocity is 0. This is going to be a key concept we're going to visit today. So the V for part A, the final velocity will be 0 when it's at its maximum displacement. Okay, so this is a key idea here. We now need to think about the SUVAT formulae that we might need to know. And so here they are. So right now we're not really concerned with the time for part A. So the time, we don't want to know it, we don't need to know it, so I'm just going to put a cross against time. So we want one of these formulas here which doesn't involve time, because we don't know time. Time can't help us out. So that's got t, that's no good. This has a t, that's no good. Nope. Nope. However, number 5, v squared equals u squared plus 2as, that does not involve a t, so this is the one we can use. So start with v squared equals u squared plus 2as. Then we can rearrange this in terms of s, so s equals v squared minus u squared divided by 2a. Now we just fill in what we know. And so we know v, when it's at its maximum displacement, that'll be 0. U, the starting velocity, is 10. And a, because it's a deceleration, we know that to be minus 2. So we just fill in what we know. So 0 squared minus 10 squared all over 2 multiplied by minus 2. And again, just colour coding it in for the hell of it, I suppose. We can now work this out. So get the calculator up. So 0 squared, I'm going to leave it out. You know, 0 squared is going to be 0, so just do minus 10 squared, which will be minus 100. All divided by 2 multiplied by minus 2. That gives us 25 meters. So maximum displacement from O is 25 meters. Part B, find the time when the displacement is reached. So for this one now, what I'm going to do is again just update what we know for SUVAT. So the displacement now we know is 25, so we can add that one in. So we can use that if we wish. U is still 10. When it's at maximum displacement, V is just still 0. A is -2. We want to work out the time. Okay, so we could use any formula if we wanted that gives us time. Now, of all these formulas we've got to choose from, obviously we can't use number 5 because 5 does not involve time. I would suggest the easiest one to use might well be the first one because it doesn't involve anything quadratic and it's less awkward. You could use 1, 2, 3 or 4, it's up to you. In fact, try it on your own if you don't believe me. So what we want here is we can use A equals V minus U over T. So if we rearrange this, we see that the time is going to be V minus U over A. And so in our case, for V we've got is 0. The initial velocity is 10 and A is -2. So if we just plug this in, we're going to get 0 minus 10 divided by -2, and you should find that that gives you 5 seconds. So that's question 1 done. Let's now have a look at question 2. Question 2, this is just to get you used to using the standard form button, because we're going to need this later on after the warm-up for doing the universal gravitation. So anyway, here's an example of how to use your class whiz in order to do a question involving the use of the standard form button. So what we're going to do here is try and apply this with this example. So try and calculate this using the standard form button. So if we were to do that, and to be honest, you don't have to use a standard form button. I'll show you how to use it though. So I'll make the screen big so you can see what's going on. Slightly too big perhaps. Oops. So in fact, I'll slide the calculator over, we'll pop it here. So it's a fraction, so we can type the fraction button like so. Then we do 1.2. Now instead of typing times 10 to the power, we can press this button here. Okay, then after the times 10, we just type in the power of 10 we want, so we just type in 13. So section it off in brackets. Then we're going to multiply this by 2.4, press this again, but now the power of 10 is -17. And again, close brackets. Finally on the bottom, we've got 6, and again it's a times 10, so press this button here, followed by 5, close it off, and then square. And we get here 8 times 10 to the -16. Now, I'll be honest with you, personally it's rare that I use it myself. Because calculators now have such like a natural looking display, here's how I'd probably type it out myself. I'd probably just type it out exactly as it looks. Now the option is entirely up to you, okay? So the choice is yours. I just do it like this personally though. 1.2 times 10, press the power button, 13, press that button there to toggle away from the power, then multiply by 2.4, again times 10, press the power button, type in the power, which is -17. Now press down to this line. This is brackets, so pop in a bracket. So 6 multiplied by 10, press the button there again, press a 5, close it off and press squared. Press equals, and you say here you get exactly the same thing anyway, so it's not that you have to use a particular method, it's just that this button has the times 10 to a certain power built into it. You can use that, or you can just do it manually using the power button like I just did there. So I'll leave that choice to you, whichever you feel most comfortable with, I'd suggest. Let's now have a look at question 3. So we're told here a circle C has equation x squared plus y squared plus 4x minus 2y minus 5 equals 0. Find the centre and the radius of C. So I'm going to write the x terms together, x squared and x terms, and the y squared and y terms, and the minus 5 on its own, all equal to 0. So now what we need to do is complete the square on the x stuff, and then the y things separately. Okay, then we'll still have this minus 5 at the end, equals 0. So x squared plus 4x. Let's complete the square on this. So we halve the coefficient of the x, so the plus 4 becomes a plus 2. We square that, then we minus off this 2 squared. So we minus off 2 squared, so we do minus 4. Over here, to complete the square on y squared minus 2y, we're going to get y minus 1, because we halve the coefficient of the y as well. We square that, and then we subtract away this term here squared. So minus 1 times minus 1 is 1, so we subtract 1. Now we can piece this together. So we have x plus 2 squared plus y minus 1 squared. Now from here, we've got a minus 4, we've got a minus 1, and we've got a minus 5. And so if we bring all of that to the other side, if we add on 4, add on 1, and add on 5 to both sides, we get that it equals 10. Now we should be able to work out what the centre is. So the centre is given from the values in these brackets. So the centre, in the x bracket, we've got x plus 2. That tells us the x-coordinate of the centre is minus 2. In the y bracket, we have y minus 1. That tells us the y-coordinate of the centre is plus 1. And the radius of a circle is just going to be the square root of this value here at the end. So the radius is going to be root 10. And so that's that one completed. Let's have a look at question 4, the final one of the warm-up. So we have here point P, which is minus 4, 3. It lies on a curve with equation y equals f of x. So state the coordinates that P is transformed to on the curve with this equation. Now this is almost a nod towards year 13. They've got more than one transformation to contend with. So first of all, what I'm going to suggest at this stage is we take it step by step. So we're starting with y equals fx. Now, when we have y equals fx, we have that this point P is at minus 4, 3. Now, what we're going to do here is think about which one of these transformations to do. So we're going to do the x minus 1 bit first, or the 2 on the outside. Okay. Now, as it happens strangely, in this particular case, we could do whichever we wish first. Okay, we could do whatever we wish. However, generally speaking, it follows something very similar to BIDMAS. So I'm going to suggest here we do the brackets first, and then we'll do the 2 on the outside after. So let's consider the effect of taking this function here and transforming it to f of x minus 1. So if we do this, remember, inside, opposite. When the change happens inside the brackets, the change is almost opposite to what common sense might tell you. And so here, we don't subtract 1 from the x-coordinates, which is what it looks like, we actually add 1 to the x-coordinates of all original points. So this minus 4 here becomes minus 3 for f of x minus 1. The y-coordinate is not affected, so that stays at 3. So now we've made one change. We've got to the f of x minus 1. The next thing we can do is go one step further and bring in this 2. So what would we have to do to go from this function here to 2 lots of it here? So from here to here, the only thing that's changed is this 2. Now this 2 is outside of a bracket. You need to remember, if it's outside the bracket, it affects y in a common sense way. So 2f means 2 multiplied by f. That's to say that the y-coordinates are going to be multiplied by 2, and the x-coordinates are not going to be affected. So this point here, the x doesn't get changed from here to here, but the y-coordinates are doubled because of this 2, so 3 doubles to 6. So the points that p is transformed to, minus 3, 6. So p starts from here, which is minus 4, 3, and it ends up being transformed to minus 3, 6. Now let's have a look at what we've got in store today by talking through the next part of the lesson. So we're going to have a look at Newton's laws of motion and apply this to universal gravitation. So what we're going to do now is discover that we can use the formulae for constant acceleration to model an object moving under gravity. So let's first see if we can state Newton's laws of motion, which were first published in 1687. So these are about 3.5 centuries old now. So Newton's first law. An object either remains at rest or continues to move at constant velocity unless acted upon by a resultant force. So that's not to say that if an object's moving, no forces are acting on it. For example, a car might be on a motorway doing 70 miles an hour. The thing here, we're not saying that no forces are acting on the car, but what we mean by resultant force is that all forces are completely balanced. Okay, so the thrust of the engine is being exactly cancelled out by the friction and air resistance and so on. Resultant force means overall force. If an object is moving at constant velocity, no overall force is acting upon the body. The second law, so the force F acting on an object is equal to the mass m of the object multiplied by the acceleration a of the object in question. This is almost always given as just F equals ma, and this assumes here that the mass is constant. So for the mass of an object being constant, F equals ma. Third law. This also is particularly famous. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction of the first body. So it's commonly paraphrased as every action has an equal and opposite reaction. So those 3 laws, which are about 3.5 centuries old, are still more relevant now than ever. Okay, so we still use them, we still teach them, and dare I say, they'll still be taught long after we've been on the planet. These are not going to go away. These are classical mechanics laws, but always have a place to be learnt from. So, say goodbye to those just for a moment, and let's have a look at the next part. So how does this apply to universal gravitation? So these 3 laws of motion apply on our scale as human beings, for apples, for objects like cricket balls, but they apply to universal objects as well, for example, planets and stars. So the scope of it is literally universal. So in terms of gravity, consider 2 masses, m1 and m2, such that the distance between their centres of mass is r. Every particle in m2 attracts every particle in m1 with a force F1. So F is proportional to the product of both masses and inversely proportional to the square of the distance between the centres of mass. And indeed, every particle in the universe attracts every other particle by the same law. So here's a little illustration showing you what's going on. So we've got M1 and M2, and F1 is acting towards M2 because M1 is being attracted towards M2. Likewise, M2 is being attracted towards M1. Now the magnitude of F1 and F2 are identical but acting in opposite directions. R here is the distance between the centre of mass of M1 and M2 respectively. So the equation for universal gravitation takes this form. F1 equals minus F2. You might be thinking here, but didn't he just say that they're equal? Well, they're equal in size, but opposite in direction. Force is a vector. Okay, so this force 1 is equal and opposite to force F2. Equal in magnitude, opposite in size. Now, G is what's known as the universal gravitational constant. So the force is some constant, which I'll mention in a moment, multiplied by the product of masses and divided by the distance that separates the objects squared. And so here's the key thing here. So we're told F is the gravitational force acting between two objects, M1 and M2, and they're the masses of the objects. R is the distance between the centres of their masses, and G is a gravitational constant. Now this is eye-watering, in fact. This is sort of hard to get your head around. It's absolutely tiny, okay? On a unit-by-unit basis, gravity is the weakest force known, okay? So the constant here is 6.67 times 10 to the minus 11 meters cubed, kilograms to the minus 1, seconds to the minus 2. You might think it's strange me saying that gravity is the weakest force known, but think about it. Your weight, okay, your legs can support your weight. However, although your weight is something you experience every single day, it takes a literal whole planet's worth of mass, in other words, the Earth, for you to feel that weight. Yeah? So gravity, it takes a load of mass proportional to how much force it generates. This constant here is not something I expect you to remember, but we're going to use it in an example in just a moment's time. So let's consider two masses, M1 and M2, as Earth and an object, respectively, on the surface of the Earth. So it's not drawn to scale. If that was drawn to scale and this is the Earth, that would be, I don't know, 10, 100 times taller than Everest. So that is not to scale, that's just showing you what it is. So it's not a speck, it's not just one pixel on the screen, which is hard to see. So the mass of the Earth has been calculated to be approximately 5.97 multiplied by 10 to the 24 kilograms. So that's pretty massive, really. That's not something you could carry home in your shopping bag. So 5.97 multiplied by 10 to the 24. The radius of the Earth as well is 6.37 multiplied by 10 to the 6 meters. Again, that's quite a radius, not exactly something you could jog in a day. And we can use these results to calculate G, which is the acceleration due to gravity, to work out the surface gravity of Earth. Okay, so we can work out the size of the force. Okay, so this here is M2. Okay, so if I have the centre of the Earth here, the force due to gravity, the weight of M2, will act directly towards the centre of the Earth like so. So the weight of any object is given by mass multiplied by gravitational field strength. So this is going to be M2G. Okay, so let's assume, first of all, that something is free falling. You might be thinking, well, I've not seen this before. How do I know that weight is equal to mg? Well, imagine you have an object Okay? And this object is falling. So just for now, let's consider that air resistance isn't really a factor. This is just a simplified idea. So if something's falling, if anything dragging it towards the centre of the Earth, if anything causing it to fall is going to be its weight, the gravitational pull, because of the mass of the Earth. So if I label that W, the acceleration will be this way. Okay, so it's accelerating towards the ground if it's in free fall. So I'm just going to put this as like a little thought bubble here. So, from Newton's second law, we know that F equals ma. So resultant force is ma. So if we consider just neglecting air resistance for a moment, we can assume this is like a vacuum or on a planet perhaps. And the force, the only force acting will be the weight. So weight equals the mass of the object multiplied by its acceleration. But the only acceleration it'll be experiencing will be the acceleration due to gravity. And so here, A is the same as G. G is the acceleration due to gravity. It's not being pulled down because some other force is pulling it towards the Earth. The only acceleration will be because of gravity. So in other words, W equals mg, because A, on the Earth, if an object is falling towards the ground, the acceleration is one and the same thing as the acceleration due to gravity. So a general result, the weight of an object, W, that equals mg. So return to our case here. So if an object m2 has mass m2, then the weight of it is m2g. Okay, so the force due to gravity is experienced by the weight, so the force is m2g. Now going back to what we had earlier, that's g m1 m2 over r squared. And if you didn't remember from before, the magnitude of G was 6.67 multiplied by 10 to the minus 11. Okay, so this is part of the reason why one of the warm-up questions was getting you thinking about standard form in terms of very big and very small numbers. And so now what we can do, if you look here, we can cancel m2 in each equation. So therefore G on the surface of the Earth is going to be big G, if you like. Big G is this. So we're going to have over here 6.67 multiplied by 10 to the minus 11. We're going to multiply that by m1. Now m1, it says here, is the mass of the Earth, which is 5.97 times 10 to the 24. Clearly my fraction line isn't long enough, so I'm just going to extend this here. And then all of that's going to be divided by the radius squared, and the radius here of the Earth. Now this varies around the planet, okay, so the Earth actually bulges slightly around the equator. So the distance from the centre of the Earth to the poles is less than the distance from the centre of the Earth to some point on the equator. But we're going to ignore this. This is just an approximation, albeit a very good approximation. So radius squared is this value here squared. Pardon me. So it's going to be 6.37 multiplied by 10 to the 6 squared. So now if we just type this into our calculator and take a bit of care of how we're typing it in, of course, this will drop out absolutely fine. Okay, so give myself a bit more space. So what we have here is that g is approximately 6.67 multiplied by 10. I'm not using this button here, I'm using my own preference, which is just using the powers, and multiplied by 5.97 multiplied by 10 to the power 24, and all of that we're going to divide by the radius of the Earth squared. So 6.37 multiplied by 10 to the 6, and that's going to be squared. So type this in, we get approximately 9.81. To three significant figures. Now, like I said, g does vary a tiny bit here and there on the surface of the Earth. The surface of the Earth can take different heights. So, for example, g, if you're standing high, may be slightly lower than if you're standing at sea level. And as well as that, like I said, g near the equator tends to be a bit less than g near the poles, because at the centre of the Earth to the equator tends to be a further distance than if you're standing somewhere closer to the poles. So because of that, 9.81 isn't always exact. And so g is often given, because this three significant figures is often too accurate in a way. It's not always true. So somewhere else on the Earth it might be close to 9.80 or even 9.79. So to make it more universally acceptable, for Earth at least, a figure which we can all agree on, 3 sig figs isn't that thing. So if we give it to just 2 sig figs, g is often given as just 9.8. Because g is almost always more than 9.75 and less than 9.849, whatever. So 9.81 might not always be true, but 9.8 meters per second squared on the surface of the Earth is pretty much always true. So that's just a bit of background as to where this number g comes from and why you might see that number cropping up from time to time, this year and next. So this is an important point here. The force of gravity causes all objects to accelerate towards the Earth. If, and this is a big if you ignore the effects of air resistance, the acceleration is constant. It does not depend on the mass of the object. So to conclude, an object moving vertically under gravity can be modelled as a particle with a constant downward acceleration of g, where g is 9.8 meters per second squared. So this asterisk is just to let you know that there is a slight variation depending on how far away from the surface of the Earth an object is located. The further away, the lesser the value of g. But this here is quite something. So if you did ignore the effect of air resistance, if you did, the acceleration of all objects towards the centre of the Earth would be constant. So sometimes obviously that's not going to be the case because air resistance does exist. So for example, if you dropped a bowling ball and a feather, for example, the air resistance on a feather is going to be significantly affecting the feather more than it would do a bowling ball. However though, if you removed air resistance by, for example, having an experiment in a vacuum or on the moon or in space, a bowling ball and a feather would fall at exactly the same rate. Hard to believe, but here's a little demonstration for you. So these are some feathers and a big ball falling in a massive vacuum chamber. And as you can see, they fall exactly together all the way from the top to the bottom, which I think, even for myself, it's quite hard to believe and quite hard to see. This isn't some fake news, this is legitimate. This is what would happen. And that just validates Newton's laws. Okay, so g, the acceleration due to gravity, acts on all objects, and the acceleration due to gravity is constant for every single object. The only times where we think actually it doesn't look constant is because of air resistance or other factors. In the absence of those factors, the acceleration due to gravity can be seen, as it's being seen here, to be constant. So let's now have a look at a worked example. So could we work out g, for example, on the surface of Mars? Well, actually, yes, we can, to a good degree of accuracy. So use the formula for acceleration under gravity to work out g on Mars. So just having what we had before, g, the acceleration due to gravity, is going to be g multiplied by the mass of Mars divided by the radius of Mars squared. So I'm just going to call this g subscript Mars. Now g, from before, we need to remember what it was. That was 6.67 multiplied by 10 to the minus 11, the universal gravitational constant. M1, 6.42 multiplied by 10 to the 23. As you can see, it's less massive than the Earth, but in the grand scheme of things in terms of the solar system, it's the same sort of ballpark. This is why Mars is often considered like a sister planet to the Earth, and in fact in many hundreds of years from now we might have a colony on Mars. I don't think I'll be around to see it, but hey ho. So the radius squared is going to be 3.39 multiplied by 10 to the 6, all of that squared. So let's work this out. So 6.67 times 10 to the power minus 11, not minus 111, sorry, multiplied by 6.42, multiplied by 10 to the power 23, and all of that divided by 3.39 times by 10 to the power 6, all of that squared, and press equals. So we get here about 3.73. So I'm going to call that 3.7 in fact. So it's less than half of the acceleration due to Earth's gravity. So it's somewhere between a third and a half of the gravity experienced on Earth. So a pretty useless joke might be, if you want to lose weight, you could always go to Mars. That technically is true, but it's not really that practical, not yet anyway. So that's just a bit of background about how these three laws extend way beyond the scope of our own planet, which I think is both fascinating and also beautiful. But anyway, in the exam, I'm going to show you some question types which you might be more likely to encounter. So this stuff about gravity and Mars, don't get too hung up on that. But these next 5 questions, which are quite difficult, these are exam grade. Do pay attention and do try and master these. So without further ado, let's have a look now at some worked examples. So here we are, worked example 1, vertical motion under gravity. So we've got a ball that's released from rest 1.7 meters above the ground. So by modelling the ball as a particle, in other words, no air resistance, let's find the time taken for the ball to reach the ground. Now I've already included, as I will do in all of these questions, the SUVAT formulae for you to reference. So that should just help speed things up and help you to be more confident in answering these questions. So what I'd suggest doing here is just maybe sketching it out, to be honest. So we've got, it's a release from rest. So I don't know, it could be dropped from a certain height of, well, it is dropped from a certain height, in fact, of 1.7. So I'm going to say here that's 1.7 high, and also I'll label it as 1.7 meters. Now it's released from rest, but the initial velocity will start very soon going towards the ground. So for that reason, I'm going to take down as being the positive direction. I'd always take the initial direction of motion, or the near initial direction, as positive. So it starts at rest, so u equals 0. And we need to find the time taken for the ball to reach the ground. Well, based on what we've done so far, and seen so far, we should now be able to work out that, well, we should now know, in fact, that g, the acceleration due to gravity, can always be modelled as being 9.8. Okay, so we're going to model this as being 9.8 meters per second squared down. And it's in the same direction as what this ball will be travelling in. So for part A, let's just think about SUVAT, so get this listed. So it's released from rest. So U is 0. It's 1.7 meters above the ground, so when it reaches the ground, the displacement will be 1.7 meters. Remember, down is positive, so it will have travelled 1.7 meters in the downwards direction. So S is 1.7. Now, the velocity, we don't know, and also we're not really bothered about it, so I'm just going to put a cross there. I don't care about velocity. The acceleration is 9.8 meters per second squared, the acceleration due to gravity. And the time taken, that's what we're asked. So the time taken, oops, wrong colour, that's already the colour for the acceleration. So the time taken, it's going to call that as t, and I'll put a question mark by it, because that's what we want to work out. So we don't care about v, so we need any formula that doesn't involve v. That does involve v, so that's no good, that's no good, that's no good, that's no good. So again, weirdly, you find that s equals ut plus half at squared is used probably more than most. So we're going to use this one now. So for a, we're going to use s equals ut plus half at squared, and we're going to fill in what we know. So s is 1.7. U is 0, so ut is just nothing, okay? A is 9.8, so half of A is 4.9. So we have 1.7 equals 4.9 t squared. So therefore t will be 1.7 divided by 4.9, and all of that square rooted. So let's just do this on the class whiz. So square root of 1.7 divided by 4.9. I'll give this to three significant figures. We get 0.589 seconds. Let's have a look now at part B. So the speed with which the ball hits the ground. And so in this particular case, I'll just return to SUVAT and list the same stuff as what we did before. So we had S is 1.7, U is 0. This time I'm going to put a question mark on V, because we want to know V. A is 9.8, and this time we can ignore T. So we use exactly the same stuff as what we used before. Let's see if we can use a different equation. So this time we want something that doesn't involve T. So which one of these doesn't involve T? Well, that one does involve T, that one does, and those two do. However, v squared equals u squared plus 2as does not. So we can use v squared equals u squared plus 2as. So using v squared, wrong colour, using v squared equals u squared plus 2as, we can now see that v equals u squared. Well, u is 0, yeah? So u squared will be 0 squared, which will be nothing, right? So we could ignore that. We're just going to have 2 times a, which is 9.8, times s, which is 1.7. So that's v squared. We want v, so I'm going to square root all of this. I'll colour code it again, just so you know where everything's coming from. Acceleration due to gravity, and the displacement is 1.7 because it's falling from a height of 1.7. So we can work this out now. So square root of 2 multiplied by 9.8 multiplied by 1.7. And we get here to three significant figures that the velocity when it hits the ground is 5.77. So we've got 5.77 meters per second. Let's now have a look at worked example number 2. Number 2, we have a ball which is projected vertical upwards again with a speed of 21 meters per second from a point O. So O is like the origin essentially, okay? By modelling the ball as a particle, find A, the maximum height above O reached by the ball, and part B, the time taken for the ball to return to the point O. So what we need here is to consider the directions of motion, and also as well, I think maybe a good idea would be to sketch a little diagram out for it. So we know that it's being projected vertical upwards with a speed of 21 meters per second squared. So what I'm going to do here is just sketch this particle, and we can say that it's got an initial speed of 21 meters per second. In fact, I'll just write that on the other side of it. Okay, like so. However, we know that the acceleration is going to be going against that particular initial direction of motion. So if I just bring this down slightly, then we know it'll go up, 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 and eventually we'll return to this point O at the bottom. And because the acceleration will be acting downwards, opposite to direction of initial motion. And obviously the acceleration due to gravity is 9.8 meters per second squared. So we can start thinking about this now. So we know that it's constant acceleration because the acceleration due to gravity is a constant 9.8 meters per second squared. So for part A, let's just use SUVAT again. So we want here the maximum height above O reached by the ball. So that is essentially the displacement we're trying to find out. So maximum height above O, that's the displacement. So I'm going to put a question mark by S, because that's what we want to work out. Now, the maximum height is going to be reached at this point. Now, at this point here, okay, the velocity is going to be 0. It's not going up anymore because it's got to its maximum point, but it's not yet falling back down. So you think about any projectile, if you throw a ball up in the air, it's at its maximum point just before it starts to fall back down. It's at the point where it's just sort of momentarily floating in the air with no speed. So it's gone all the way up, but it's not yet fallen down. So at this point here, the velocity is equal to 0. And so we can fill this in. We know that the initial velocity rather, is 21 meters per second. And again, I'm taking here up to be positive because I always think it's a good idea to take the initial direction of motion as the positive direction. So U is 21. Wrong colour again. What am I like? Silly me. Anyway, V is going to be 0. When it's at its maximum height, V is 0. It's not yet falling down, but it's gone up all it can. So V is 0. That's the maximum height when V is 0. A is minus 9.8. The acceleration is downwards because of gravity. It's opposing the initial direction of motion. So A is going to be minus 9.8 because it's going down. And for part A at least, we don't need to consider the time. So based on what we know and what we want to know, we can see here that time doesn't feature. So time doesn't matter. So which one of the SUVAT formulae doesn't involve time? Which one can we use? Well, this one here involves time. That's no good. This involves time. That's no good. As do these two. So again, what we're going to be doing is using number 5, v squared equals u squared plus 2as. So let's just write this out. Okay, so we want to work out s. So let's get this formula in terms of s. Let's make s the subject. So s equals v squared minus u squared, all divided by 2a. And now we can substitute in what we know. So we know that u was 21. V at its maximum is 0. So I can use that v is 0. And 2a, well, a is minus 9.8 because that's the acceleration due to gravity. So let's just plug those values in. So if you really want to, you can write 0 squared. In fact, I'll do it now just so you can see you can do if you really want to. And minus 21 squared, all divided by 2 lots of negative 9.8. Let's see what this gives us. So 0 squared minus 21 squared, all divided by 2 multiplied by minus 9.8. That gives us 45 over 2, which is 22.5. 22.5 meters per second. Apologise, I had a total mind wobble there. I don't know what I was thinking meters per second. It's asking for the maximum height, so it's going to be in meters. I do apologise. This is going to be in meters, so forgive me. It's not a speed, it's just meters. Silly me, forgive me. Okay, so 22.5 meters. Now part B, the time taken for the ball to return to point 0. So I'm going to just rewrite the SUVAT formula down, because we need here when it returns to point 0. So when it returns to point 0, s is going to be 0. There's going to be no displacement when it gets back to where it started from. U is still 21, because it still went up with an initial speed of 21. V, when it gets back to point 0, we don't know what V will be, and we're not asked to work out what V will be. So I'm going to just ignore V, put a cross by it, we're not interested. A will still be minus 9.8, but this time is what we're interested in. So from this, we need an equation which does not involve V. So going back to these 5 SUVAT formulae, which one doesn't involve V? In other words, which one can we use? That involves V, so that's no good. Nope, that's got a V, as does that one. So to find the time, what we can use is s equals ut plus half at squared. So that's what we're going to go for here. So let's fill into this formula what we know. So s is 0. So ut is now going to be 21t because u is 21. And plus a half at squared. So in our case, a is minus 9.8. And t squared, I just leave as t squared. So let's just simplify this slightly. So 0 equals 21t. Now half times minus 9.8, that's minus 4.9 t squared. We now have a common factor of t at both sides here, so we can factorise out about t and say it's t brackets 21 minus 4.9t. So obviously, one solution, as you can see to this, is when t is equal to 0. That's the trivial solution, because it starts out when t is equal to 0. So how long it takes for it to return to 0 is going to be given by this value of t here. So we set this equal to 0. When this bracket is equal to 0, it will equal 0 as required. So 0 equals 21 minus 4.9t. So therefore, t is going to equal 21 divided by 4.9. And if we did that, what we're going to get is on top 21 and on the bottom 4.9. And we get for this, as you can see, to three significant figures, 4.29 seconds. So that's question 2 done. So that's 2 questions down. Let's now have a look at the third question, worked example 3. Worked example 3, it takes things up another notch in difficulty. So this time we've got a ball going vertical upwards again, initial speed 18 meters per second from point A, but this time look, it's 5 meters above the ground. So it says, given that the ball is modelled as a particle, calculate the time of flight of the ball. Okay, so time of flight, all this means, it doesn't mean the ball's going to, grow rings and fly away. It just means how long it's in the air. How long the ball is in the air for. Now at this point, because it's a bit more of a complex situation, I'd strongly recommend just doing a little diagram for this one. So if you imagine this is the ground, this time it's not gone from the ground, it's gone from a point A, which is 5 meters above the ground. So what I'm going to do here, just imagine drawing where it's been dropped from. Okay, so it's been launched from here, let's say. I'm going to say that this distance here is 5 meters. That's 5 meters. And again, I can't seem to get my arrows going straight today, which is a tiny annoyance. It's not a major thing, but still. So it's gone up here, straight up, with initial speed of 18 meters per second. Who knows if it went up from a square shape or a building or just something which is 5 meters high? Who knows? And to be honest, who cares? The main thing is I'm just trying to illustrate it's not gone from ground level. So it's going to go up, reaches a maximum, then falls back down to Earth here. So the initial direction of motion is upwards. So again, I'm going to take up as positive. So the initial point is 5 meters above the ground. So if up is positive, okay, then when it lands here, it's going to be 5 meters below the point from where it was launched. So if we think carefully, we can formulate what we know in terms of SUVAT. So we want the time of flight of the ball. So because we want the time of flight, okay, we're interested in time. So I'm just going to go for time and put a question mark there. We want to know the time. We do know A in terms of vertical motion under gravity. So A is going to be minus 9.8. I'm assuming here that up is a positive direction, and obviously acceleration due to gravity is going down because things accelerate towards the ground, quite obviously. So that's 9.8 meters per second squared. So minus 9.8 because it's going towards the ground, opposite in direction to the initial direction of motion. Now, when it ends the time of flight ends when it hits the ground. That's when it stopped being in the air. Now, when it stops being in the air, it hits the ground, and it hits the ground 5 meters below where it was launched from. So this again is just a case of interpretation. and carefully considering what we know. When it hits the ground, okay, S is going to be -5. It's going to be 5 meters below from where it started. The initial speed is 18 meters per second upwards, so we can fill this in as well. The end velocity, the speed when it hits the ground, we don't know, we're not asked for it, we don't need to know it, so we can just cross it off, we don't really care. So now we need an equation which doesn't involve v. We don't want to work out v, we don't know v, so let's just cross off anything involving a v. That's got a v, and these two, and again, like you see, s equals ut plus half at squared, that seems the most common one to use. So I'm going to go for this one. So let's fill in what we know. So S, this time, is -7. Sorry, -5 I mean to say. I don't know why I said 7. So -5 equals ut, so that's 18t, plus a half, multiplied by 9.8, multiplied by t squared. So we have -5 equals 18t. Half multiplied by -9.8, that's -4.9. So we get -4.9t squared. So if we now rearrange this into a standard form of a quadratic, I'm going to suggest what we might want to do here is just get everything onto the left-hand side of the equation. So we can add on the 4.9t squared, subtract 18t, and of course we have -5. So now what we can do is work out what t is. So there's a couple of ways of doing this. We can either use the quadratic formula, or we could use the class whiz. So once you've got to this stage here, you're allowed to, take it easy. You're on the home straight now. So I'm going to go for the class whiz, just as a gentle reminder to you of how to use it to solve quadratics. So what we do here, we start on the main menu, press menu. We need to scroll to option A, equation/func. So press equals. So polynomial, press 2. Now a quadratic, the highest power of the variable is 2. So we select number 2, and then input what we have. So the coefficient of the variable squared, the coefficient of our t squared is 4.9. So we type this in. The coefficient of the t is -18. So again, we press this in like so. And then, of course, we have -5. So we type in -5. Press equals. The first value is 3.93. So t equals 3.93. The next one, if we press it again, well, that's a nonsense. Okay, we can't have a negative time. So we reject that. So we can write it down if we really want to. So -0.26-ish to 2 decimal places. As I say, we can reject that because that is an impossibility. And just put, to conclude, therefore the time of flight is, to 3 sig figs, 3.93 seconds. Just under 4 seconds time, it returns and hits the ground. So it's in the air for roughly 4 seconds, which I'm sure you can agree, if you imagine just throwing something up as hard as you can, if you had a good throwing arm, it could be in the air for about 4 seconds potentially. That's question 3. Number 4. A ball, again, is going upwards with a speed u from point x. The greatest height reached by the ball is 42 meters above x. By modelling the ball as a particle, so no air resistance required, find A, the value of u. So again, what I'm going to do here is suggest that we do a sketch. So we've got here the particle starting out at point X. So I'm just going to do a sketch here, like so. This is going to be where X is at. Now it's going upwards with speed u. Let's label this u. And it says the greatest height reached by the particle is 42 meters above X. So it's going to keep going and going and going higher and higher, higher and higher. Now you might be thinking when I'm doing these diagrams, why am I always doing it like a U shape? Well, it could be going straight up and straight back down. But if I did that, I'd have the same information superimposed on other information. So I'm just doing this for clarity, so that I can label the different points of the path of motion differently, rather than all being superimposed on the same straight line. Anyhow, so we are told that the maximum height it goes above X is 42 meters, so we can label this in as well. So that's 42 meters. And we need to calculate the value of u. So when it gets to its maximum height, this is again mentioning the key concept again. With the maximum height, the speed is momentarily zero. It's not going back down to the ground, but it's not going any higher either. So at this point, we need to just remind ourselves that velocity is just for that moment in time, zero. So for part A, we need to work out the value of u. So let's just write down what we know in terms of SUVAT. So we want to work out the value of u. So u is what we want to find. I'm just going to put a question mark next to u to just clarify that that's what we're wanting to find out. Now, based on what we know for part A, the displacement at the maximum is 42 meters, and again, like I keep mentioning, I'm taking upwards to be positive. The initial direction of motion, I think it's easiest if we just take that to be the positive. So S is going to be 42. And we know this from what the question says here. Now V, when it gets to the maximum point, is 0. So I'll label this in as 0. The acceleration always, when we're talking about free fall or gravity, the acceleration is going towards the ground, towards the centre of the Earth, at 9.8 meters per second squared. I'm thinking ahead of myself. The acceleration, because it opposes the initial direction of motion, the acceleration is minus 9.8. It's acting towards the ground, whereas the initial direction of motion is away from the ground, upwards. Now at this point here, we don't have a clue about the time, nor are we asked about the time, so I'm just going to put a cross there, just to let us know that we don't really care about t for this part of the question. So in other words, for part A, we need to use one of these SUVAT formulae which doesn't involve t at all. If it involves t, it's going to be no good to us because we don't know t. So that's no good because it's got a t in it. This has a t in it, so that's no good. No good, no good. However, as ever, you'll find one which will work. So in this case, we want v squared equals u squared plus 2as. So that's one we're going to apply and use. Now I just plug in what we know. So v squared is 0 squared. U squared, well that's what we're wanting to find out. Then plus 2 multiplied by a. A is minus 9.8. Let's move this slightly to the other side. And S is going to be 42. So as you can see, this here is going to be negative. Okay, so if we work this out, it's going to be something negative. So I'm going to just write this as 0 equals u squared. Now if we get this on the calculator, 2 multiplied by minus 9.8 multiplied by 42, that gives us minus 823.2. So if we now add 823.2 to both sides and then square root, we'll get what u is equal to. U will be the square root of 823.2 so if we just square root 823.2, give it to the appropriate accuracy, so round it to 3 sig figs if in doubt, so we get 28.7 meters per second squared. Sorry, meters per second. So the value of u, 28.7 meters per second. Now part B, for total time for which the ball is 40 meters or more above x, what we can do here is use SUVAT and work out the times when the height above x is exactly 40. So set s to be 40. Okay. So what I'm going to do here is just add to the diagram. Okay, we'll find two values of s. One value will be here. One value will be here. So I'm just going to call this T1 and T2. So it'll be 2 times when s is 40. Between those times, the distance between those times will be when the particle's above it. So just fill in what we know again. So the initial velocity, well, we now know it's 28.7. However, let's give it more accuracy so we don't incur any rounding error. So I'm going to go for 28.69146. 28.69146. We worked out this from part A, so we may as well use it if we can. So at T1 and T2, we don't know what the velocity will be. At T1, the velocity will be positive because it'll still be going up. At T2, the velocity will be negative because it's coming back down, but we don't have a clue what those particular velocities will be. So I'm just going to put a cross there because we don't really know what it's going to be. And maybe we don't need to worry about that. A, as ever, is going to be minus 9.8. Okay, it's going to go towards the ground, so it's going to be acting against the initial direction of motion. Now T, in this time, we do want to consider, so I'm going to put a question mark next to T. And so we need a SUVAT formula which doesn't involve the need for V. So what could we use? Anything with a V in it isn't going to be any good. And again, it seems to be s equals ut plus half at squared is going to save the day. That seems to be a very common formula which is used time and time again. So we start with this and we can fill in what we know. So s, we're going to go for 40. So 40 equals ut, so 28.69146t. Now half times a, that's going to be half times minus 9.8, so it's minus 4.9 t squared. Get everything onto one side of the equation, so I'm going to leave it all in terms of a minus 4.9 t squared, and plus 28.69146t, again minus 40 off, equals 0. So at this stage we've got our choice. We can either use a quadratic formula or maybe even the class whiz. Okay, so if we use a class whiz for this, so menu, scroll to option A, equation slash func, press equals. Polynomial is what we want, degree 2 because it's a quadratic, and just type in what we know. So here we've got minus 4.9, press equals. The coefficient of the t is 28.69146, press equals. The constant term is minus 40. Press equals again. So we get the first value of t is 3.566. That'll be a 6, rounding it. So 3.5666. 3.5666. I'm going to round this in the end to 3 significant figures, but for now I'm going to give it to more, so no rounding errors incurred. So 3.5666, press again, we get 2.2888. So again it seems a trio of digits each time. So therefore, time when it's above 40, above 40 meters, for 3.5666 minus 2.2888, and now I'll round it to something more appropriate to 3 significant figures. So just going back to what we had earlier, so 3.5666, 2.2888. So I'm going to go back to menu option 1 to just do the normal calculation. 3.5666 minus 2.2888. Press equals. Now we can round it to an appropriate degree of accuracy. We get about 1.28 seconds. So it's above 40 meters. It's 40 meters above x for just over a second. So it just goes above, stops momentarily, then comes back down and passes x just after a second from when it went up past 40 meter point. So that's it for question 4. So one more and then we're done and it'll be over to you. So here it is, question 5. So we have a ball A that's falling vertically from rest from the top of a building 60 meters high. However, at the same time as A begins to fall, another ball B is projected vertically upwards from the bottom of the building with speed 20 meters per second. A and B collide. So it says here, modelling both A and B as particles, so no air resistance, find the distance of the point where A and B collide from the bottom of the building. So already this is quite a out of the ordinary question, and it might seem to be quite tricky. It's not actually quite as bad as what it might seem. What I would suggest we do is to sketch a carefully labelled diagram and take it from there. Okay, so this building here is 60 meters high, so I'm going to label this information in before we start. Okay, so that's 60 meters. So that's one thing. And we've got 2 different particles here. We've got A, which is falling from a building which is 60 meters high. So I'm going to model first of all A. So A starts from here and is falling down. But the initial speed of A is that it's at rest. Okay, so because A is at rest, its initial speed is 0 meters per second. Meanwhile, we have another particle, B, that says here that B is going upwards with a speed of 20 meters per second. So as A is falling, B's going up in the same direction. Well, same plane anyway, it's going to collide, because it says here that they do collide. So what I mean says the opposite direction, but they will be on the same path. So that's got a speed of 20 meters per second. What happens here is we're going to collide. So I'm just going to do like a pretty poor sort of collision little graphic here. I can't draw to save my life. I was never that good at art, sadly. But anyway, we're going to collide at this point. So what we need to work out here, the question it's asking is, find the distance of the point where they collide from the bottom of the building. So if they collide here, what we're trying to work out ultimately is this distance here. I'm going to call this h. Okay, because we need to work out the distance of the point where they collide from the bottom of the building. So measured from the bottom going upwards. That's what h is. Now we've got two different particles like I keep mentioning. We've got A here and B down there. So I'm going to consider separately SUVAT for both A and B. So first of all, for particle A. Now A, the first direction it's going to travel in is going to go downwards. So I'm going to say down is positive in relation for A. Let's think of SUVAT in terms of A. Now for A, okay, its initial speed, it's falling from rest. So for A, initial speed is 0, so we can add this in. Now the acceleration for A is 9.8. It's going to go downwards after being from rest. So the acceleration due to gravity, which is going downwards, is in the same direction as we're taking to be positive, at least for particle A. Okay, so we can take A to be positive, in fact. The time, we're not really sure about the time, to be fair. But what I'm going to do here, I'm going to label the time big T. So big T is when they collide. So I'm going to just make a note here that they collide at time T. Okay? Now the displacement for A, well we've labelled here that the point they collide is going to be h, the height from the floor to where they collide. So for A though, how far does it travel? Well, we know this building is 60 metres tall, so in terms of h, what's the distance it's going to travel this distance here? Well, if this is h and that's 60, then this distance here will be 60 subtract h. That's what we're going to label in for the displacement of A when it collides with B. The displacement is 60 minus h. And as I say, we don't really know V, and we're not asked to find V, so I'm just going to put a cross through V. So for A, we need one of these formulas that doesn't involve V at all. So that one does involve V, as does that one. So again, we're having to rely on good old reliable S equals ut plus a half at squared. So we're just filling in the information we got. So the displacement for A is 60 minus h. U for A, the initial speed of A is 0, so we'd leave 0t out of it because ut is 0t, which is just 0. And then half at squared means half multiplied by 9.8 multiplied by the time, which we've been given as t, squared. So if we now just neaten this up, we get 60 minus h equals 4.9 t squared. So in other words, rearranging in terms of h equals 60 minus 4.9 t squared. And so that's what we get for A. It's not very well done. I'll just try that again. So this is just for A, which I'm putting into its own bubble. You've guessed it, we can now do the same for B. So for B, let's apply SUVAT in terms of B. So for B, the displacement for B as well, I'm going to take the initial direction of B, which is going up, to be the positive direction. I'm just going to say that upwards for B is positive. The displacement of B when they collide is h. Okay, so that's h. The initial speed, the velocity rather, of A is 20 meters per second in the positive direction, so u is 20. The final velocity when they collide, I don't know it, I don't need to know it. The acceleration of 9.8 meters per second squared is opposite to the initial direction of motion for B. So A, in B's case, is minus 9.8. And again, they start the motions from the same time. So again, I'm going to call time big T because they set off at the same time. So again, I can label in what I know for particle B. And U for B, I need a different colour here. I'm going to go for, what colour should I go for? I'll go for this one, very similar to the colour I've used for S. Anyway, never mind. So, for B, again we don't know V, so we can use S equals UT plus a half AT squared again. So for B, S is going to be H, so we put H. U for B is 20, so we put 20, then our T is capital T, so 20T. A is minus 9.8 relative to B, so half of A is half of minus 9.8, which is minus 4.9. So for B, we now have another formula in terms of H. So H equals 20T minus 4.9T squared. So what we can do now is we can put these two together. So from A, we had this expression for H. We have that H equaled 60 minus 4.9T squared. And now from B, we've got this. So if we put these two together, and just give ourselves a bit more space, then what we're going to see here is that therefore this version of H, which is 60 minus 4.9T squared, must equal what we have here for H, which is 20T minus 4.9T squared. And as your luck would have it, the 4.9T squareds will cancel on both sides. So if we add 4.9T squared to both sides, this one and that one will cancel. So we're left with that 60 equals 20T. So therefore they collide when T equals 60 over 20, which is 3 seconds. So we're almost there now. We need to recall the question asked us where they collide in terms of the height above where the building starts from. So we need to work out H. So now we know that T is 3 seconds. We can substitute this in back to one of the starting equations for H. So now we know that T is 3. we can sub this in for h. Sub into, let's go for, I'd suggest this one might be easier, sub into h equals 60 minus 4.9 t squared. So therefore h is 60 minus 4.9 multiplied by 3 squared, because we just worked out that t is 3 seconds. Try this on the calculator and we'll work out what h is. So h equals 60 minus 4.9 multiplied by 3 squared. Press equals, and to get it into a decimal, we've got 15.9 meters. So we're going to hit 15.9 meters up from the base of the building. Quite a difficult question, no doubt, but not one which can rule out being asked in an exam situation. So the main thing is to get good at these questions, practice, 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 as with anything in life, pretty much. So on that note, it's now over to you to try some of these on your own. So if you turn to page 151, where you'll find exercise 9e in the Stats and Mechanics book, try questions 1 through to 6, then the problem-solving type question, question 10, then 11, 12 and 13. Quite a lot to be doing there, but it will do you some good. So you know the drill by now. Check your answers as you go. If you make a mistake, try and use the answers and work backwards to try and see where you've gone wrong. If you're still struggling, ask someone you sat next to or near to. If you're still struggling, ask me, either on an email, in person, or even via the video comment section. Do feel free to subscribe. Thank you once again for listening. I do genuinely mean it. I am grateful for it. Take care of yourselves and hope to see you all soon. So once again, ciao for now.